that thing is converging. So what you'll do is you look at differences to see if those differences are getting smaller than a tolerance. But if it turns out that S is a real number, we say that that infinite series formed by those partial sums converges. And it's denoted by this. There's nothing that just drives me nuts when someone writes this and starts using it, doing algebra with that thing. Like, that's just notation. It's like just like it belongs on just a t-shirt. It has no other purpose other than that. Like, don't do algebra in this. It's the partial sums. That's the definition of what we mean by a series. So when you talk about, is a series? Well, series are sequences, really. That's all they really are. So backing up here, just to go over it again. I start with a sequence. I take the first element of the sequence, and that's my first partial sum. The second element is the sum of the first two. The third one is the sum of the first three. I line them up, and I get a whole new sequence. That's exactly how you do it when you're programming. So you run a loop and catch the next one. You're actually calculating the partial sum in numerical analysis. That's what you're doing. And then the k partial sum would be the first k terms added. So you have to stop in a program. You'd have to tell it, like, run the loop for 50 iterations or something. But you'd have the 50th partial sum, the kth partial sum. So that forms a new sequence. If that sequence converges, we say that infinite series converges. It's called an infinite series, but the definition is it's the sequence of partial sums. So if that converges, we say that the infinite series formed by those partial sums converges. That's the language we use. And it's denoted by that. There's all kinds of trouble you can get into if you start doing algebra inside that infinite series. They show you some of those things. I think they should. Do they do like one day here for infinite series? I don't know. I usually take a longer time in those classes just to do infinite series because there's like weird stuff that happens if you start to do algebra inside that series, that notation. You can make weird things happen. Okay, so I gave you those definitions so that I can give you another example. Here's my third example. Suppose I got a sequence. Vectors are the entire sequence. One vector is an entire sequence. And I know that the restriction on those sequences are that I can square sum them, and that square sum converges. So just like I showed you before, S1 would be A1 squared, S2 would be A1 squared plus A2 squared, S3 would be A1 squared plus A2 squared plus A3 squared. If that series converges, and I define addition by component-wise addition, and I define scalar multiplication by component-wise scalar multiplication, that thing is a vector space. And each vector is an infinite sequence. So what's an example of a vector that belongs in there? Because you're going to ask me. This one belongs in there. Because the square sum is 1. And it converges. And this one also belongs in there. Same reason. And guess what? These are the basis for that vector space. There's an infinite number of them. You keep going. So it's just like, I don't know if you're learning this in strength, but it's just like the E1, E2 that you have. It's the same thing, but now there's an infinite number of them. So this is not going to, like, the matrices and all that stuff will work here. Well, you could have infinite matrices. So E is a vector space over the field R. And this was exactly my talk that I gave in electrical engineering. I was actually showing something with these infinite sequences, and I was calling them vectors. And they're like, they're not vectors. Like, yeah, they are. They're vectors. They are vectors. There's a lot of confusion on both of our sides.
So because you showed that it can be added and multiplied.
I have to first define that, right? Once I define that, what I mean by that, then it satisfies that checklist of 7 properties.
So to make the next, to make this statement on the next slide, you have to go through the checklist.
Yeah, but it's a really long, boring proof.
Okay.
Right?
But you would.
Yes.
Okay.
And I needed this part of it. I needed this part of the second part, that's convergence of the square sum. I needed that to actually go through that proof because the associative properties and stuff don't work. If you actually remember this from when they cover infinite series, they will take negative things and then show you that I can get things to, if I rearrange things, I can get different outcomes. So weird stuff can happen if you don't have some kind of properties put on those series. By the way, 1 over n is in there. I actually asked you to calculate something with 1 over n. That's one of the things they show you in Calc Plus, that the series 1 over n converges. 1 over n squared converges. Right, 1 over n is the harmonic series, and it doesn't.